Thanks for the invitation to present about our work in this area. And I want to say good morning to all of the audience from sunny Arizona. It's 75 degrees outside, so we are enjoying very good weather. And this is the setting. This is the context from where we do our work in Arizona. So you see the title there, and as Sean pointed out, this is part one. This is only dedicated to the mechanical and electronic components, and data analysis will be presented a week from today. So I want to recognize people that are important in all this work that we do, and our partnership with USDA, ARS, and the Arid Land Agricultural Research Center, ALARC, in Maricopa, Arizona. Mike Gore, now with Cornell University, Jeff White, Andy French, Kelly Thorpe, and Bob Strand. This is a team effort, and I will emphasize this in different times of my presentation, that we work in collaboration. That's when we get the strongest and the best output of our work. We divided our presentation in three main parts. Part number one will be platform development from the mechanical standpoint, just a description of those mechanical components. I'll speak about the field vehicle and things related to the motion of the vehicle inside the field. And I'll describe about the sensor frame that we use to collect data continuously. Then in part number two, I'll be a little more specific on electronic components and from the hardware perspective. So plant sensors is a big one, and GPS it's an important component of our work. So I'll spend enough time talking about GPS. Third part will be handled by John Heun. This is about data collection from the hardware and software perspective, and his talk is going to be focused on system integration. So before I move to the next slide, I want to say that we thought about this presentation and the materials that we have to deliver to a non-engineering audience. That's our challenge. That's our objective. But once in a while, it's just important that we are specific in what we're talking. So if there are questions, let us know. You can contact us, and we can answer perhaps at the end of the seminar today. So our objective really goes on sharing some of the experiences and tricks, if you will, that we have learned over the last 3 to 4 years of collaborative work. So we want to share this information with people. We want to present cases of flexibility in design and functionality of system integration. Those two are key phrases in our work: flexibility and functionality. All right, so to set the context in a image form, this is what we're talking about. This is a field-ready system that we developed here in Arizona for continuous plant data acquisition. So like you see in that case, the picture, there's a driver moving this vehicle through the field, and in the front, there are sensors and all kinds of instrumentation mounted. So we're going to be describing what you see there in this picture, and we're going to also be describing the operational side from the software perspective. Okay, so let me start with a general description of a high clearance vehicle. I listed 8 key features of high clearance vehicles. So first thing to mention before I go into those points is that this vehicle has been designed as a sprayer. That's the function that it has in commercial fields. We have modified this type of vehicles to do this function of high throughput phenotyping in the field. So going to the list of key features, I listed number 1, the front and back frames. You know, in sprayers, we call those frames, we call them booms. That's the term used to describe those. So either I say frame or boom, I'm talking about the number one in the picture, in the left side of the picture. That's the frame that moves up and down, carrying instrumentation through the field. Those machines commonly come with hydrostatic transmissions. They're good characteristics of that type of transmissions. We can set our speeds constant with a constant flow of hydraulic fluid. There's articulated steering. So these machines turn by articulating in the middle of the machine. So we can do turns in a reduced amount of space. They're diesel engines most of the time. That's number 4, and that brings a very solid power train for the system. There's hydraulic power available in case we need to provide power for any actuator to move up and down or sideways. There's also supply of DC power, which comes handy when we want to provide we need to provide power for all the electronic systems. We only need to be concerned about regulating power and protecting the instrumentation from overload electrical charge. And as you see, mechanically, these are very hefty units. And as far as carrying instrumentation through the field, we have an ample payload capacity. So we're not limited by the weight of the instrumentation. That starts to see as a difference between remote sensing and these proximal sensing systems. Number 8 says very high center of gravity. So number 8 is something kind of special, kind of different, because what I'm trying to convey here with number 8 is that these units, as they are so the frame is so much high, elevated from the ground level, the physical and mechanical aspect of these machines makes them more unstable as you compare it with another vehicle that might be closer to the ground. Okay, so the centrifugal forces acting on the axles, if these machines are not well operated, there can be potential consequences in overturns or side turns of these machines. So before I get into more description of these units, I just dedicated this particular slide to mention about preventing side overturns with these machines. So we are very keen on safe operation of farm equipment, and this is one good case that we are developing guidelines, and we want to make sure that if you get one of these units to operate in your fields, you do it consciously with enough attention to the detail of safety. And the first point is that there's regulation. There's the OSH Act from 1970, I believe. So rollover protection units are required. If they're not put in these units, actually it's against the law. You need seat belts. Seat belts in combination with rollover protections is a good thing to have. The third point is one that we have different takes to it. It's a qualified operator, and the point here is that you probably want a good operator to move this machine through the field and be comfortable moving this machine. But at the same time, perhaps that person is not qualified from the electronic on the use of electronics. So you need to find a balance. You need to find a way where you have a good operator that knows what he or she is doing in the field, but also that can operate the control systems in the vehicle. Frequent inspection of tires and frame integrity. pay attention to the field conditions and the road too. We want even ground conditions. Wheel spacing, avoid high speeds and sharp turns is also a good thing to observe all the time. And among all things is if this is not in your background, consult with a machinery expert before you start deploying these systems in the field. Okay, now let's go into the material. This is our vehicle, the one that we use, and we have implemented this vehicle in many different settings. So the main feature that I want to bring with this picture is the front boom, which we also see another boom in the back. And you can see how those frames can move up and down. We favor the use of the front boom because when we put instrumentation on that boom, the forward placement of the sensors minimize plant disruption. So in other words, we collect data on those on plant conditions before the rest of the vehicle reaches those plants. So we minimize disruption by using that approach. Now, those booms can move up and down, and so we have vertical position adjustments possible. And one thing to see here as I move from slide back and forth is that the whole frame moves up and down. All of the sensors and everything that is attached to this frame will move all in one motion. That's not always the desired situation. So let me now move into frame adjustments that we have implemented in these booms. So I'm calling this sensor mounting using cultivation tooling. So the components that I'm highlighting here, number one is the use of 2 1/4 agricultural diamond bar, because with those bars you can then use clamps and shanks that are used for cultivation operations in the field, and they fit really well with these bars. So number one is a square bar of 2 1/4 inch on the side. Number two is clamps that we can attach to these bars, and those clamps will have set bolts, and those set bolts, which you see in the pointer number 2, are there to fix the position of the shanks, either round or flat shanks. So with these adjustments, what we gain is individual control of vertical and horizontal position of individual sensors. So let me demonstrate this to you. We have this sensor that is this is a housing for an ultrasound sensor for displacement measurements. And what I can do now is I set the bolts to a given position so I can move up and down, and the rest of the frame remains in the same position. So that's one type of adjustment that I can gain with cultivation tooling. Now another type of adjustment is front to back. So I can have this sensor moving front to the front and to the back. Again, and the rest of the components remain in the right position. Now another adjustment that we can have with this hardware is horizontal adjustment in the rotation side. So we see how this sensor, we can set it to whatever angle we want to. Again, all independent of the rest. Also, we have sideways adjustment on that frame. So we can move this sensor to any position that we want in that frame using the set bolts and the clamps at the bottom. All right, so that's the end of part number first part of our presentation. Now section 2 I'll cover some instrumentation hardware that we use in this platform. So proximal sensing approach to capture biophysical characteristics of plants. I have three types that we will be explaining with more detail. So the first one is the thermal response of the canopy, the plant canopy, and we use infrared thermometers for that purpose. We also record light reflectance characteristics of the crop with active light sensors. We also measure something on the architectural characteristics of the plant. We use displacement sensors like this ultrasonic sensor on the bottom of this slide, and we have only one dimension captured, so we can determine plant height very easy. We have developed an algorithm to make that more accurate, and there's we will mention about efforts to bring information on plant architecture from 3 dimensions. So that's still work in progress. We also have used extensively laser sensors like the one at the bottom right side with very good results too. On sensor selection, we have worked over a list of what we call critically important specifications of sensors, things that need to be studied before selecting one particular sensor. And the first one that we deal with all the time is communications protocols. Are those sensors communicating serially or with analog signals? And if it's serial communications, is that RS-232 or RS-485, or the one that we see more often now is SDI 12? So those are important aspects to consider. Field of view is also one very, very important one, because just think about it. You have different sensors mounted on a vehicle, and if they see a different path, a different track at the at the bottom where the plants are located, so that tells you right there that you have to have different vertical adjustment of the sensors. Range of operation. Sensors, there are parts of the in the range, there's parts that are measuring things with accuracy, but sometimes they can get to either too close or too far away, and the accuracy diminishes. So you need to observe what is that proper range of operation. Input power. We obviously prefer sensors that use direct current DC power, and in the range from I don't know, 12 or 24 volts, we can handle those easier. Response time is a very, very important one, because you can think about these platforms moving through the field, and you want to collect data as that platform is moving. So ideally you want a fast sensor. The output format is also an important one, and rugged design, something that you can take to the field and will perform accordingly. So this is a schematic of the system that we have put together, looking at spectral sensors at the front, looking at sonar transducers for plant height at the very back, numbered from 1 to 4 from left to right, IRTs mounted with in different positions. So we have, in this case, 8 IRTs mounted. Let's take a quick look at these sensors from the same picture and describe some of their specs very briefly. So first, let me start with the canopy thermal response with IRT sensors. So we're using these Apogees sensors, infrared radiometers. They have a particular section in the electromagnetic spectrum where they collect they're sensitive to. They're 38 degrees field of view. We have tested vertical or 30 degrees forward inclination. They have analog signals, And the last point that I'm bringing here is the response time of less than 1 second. That's the manufacturer's description of response time. So that tells you right away that you really have to confirm that this is fast enough for your operation or not. Plant canopy spectral response with light reflectance sensors. We're using crop circle, ACS 470, 32 degrees field of view. You can change filters to your applications. We chose to use 670, 720, and 820 nanometers. Now these work on an RS-485 network, and they're relatively fast. We are using these at 5 hertz, and the asterisks mean our own experience, and we have good success with at 5 hertz updates. Displacement sensors, again with these sonar transducers, we used this particular type brand, Pulsar 3dB, 12 degrees beam angle. Now that's not that critical for a sonar transducer, but it still has, it's telling you there's an area where there's maximum accuracy. The output is an analog signal, so it's easy to record, but there's one point here. The signal is updated based on an internal controller, internal chip that we have no control over. So how fast it's going to update information depends on the conditions that it's sensing. So we've seen that we have 2 hertz, twice a second. We can have reliable updates. Faster than that, sometimes, and sometimes we don't. GPS. On the GPS side, again, this is critically important to our work to use GPS to reference the location of the information. What is it? Where in the field is coming? Which row, and which at what point along the rows. So GPS, it's really important for our work. We have used this Outback 320 GPS RTK, real-time kinematics. This is the ultra-precise systems. We're using GNSS. The only thing to know about that is that these receivers can track many more satellites from different constellations. So the accuracy is improved by that. This particular unit is the board inside is built by Hemisphere GPS. GPS work with serial output, so you need to deal with those signals in a different way. And John Heun will elaborate on that aspect too. The messages or the strings, the serial communication, it follows a code we call the NEMA code, and we're using different strings. In particular, GGA and RMC gives us position and gives us direction information. Accuracy, we are certain that we have within 1 centimeter horizontal accuracy or better, and on the vertical position we have twice that accuracy. So it's what I'm saying is not as accurate. You lose some amount of accuracy and looking at the vertical position. John also will have a brief time describing why it is so important that we know the vertical position of that antenna as long as the horizontal coordinates of the antenna. Okay, this is my last slide before I pass this on to John, and this carries many messages that I have for the audience. First, to make the point that new machines in production ag are coming with GPS controlled navigation systems. And what's not known, or I frequently hear that people are not aware, is that the GPS signals that are feeding those ultra-precise systems, those can be also output to other devices. So the message is the following. If you have access to a machine with RTK, ultra-precise level for navigation purposes, very likely you can then obtain those signals with that high level of accuracy without having to invest in a receiver that is very costly. So that's the message. That's the picture here with a Trimble FMX on the left. Take a quick look at the screenshots that we added on the right. And the first thing to look in the top screenshot is that the GPS quality is fixed, and you see that on the right says corrections RGK. So at that point in time when we took this screenshot, we were receiving a highly accurate position string. At the bottom you see that this slide says GPS output settings, and it's listing the different strings that we can choose from. So we can choose what strings to output, and we can also choose how fast those updates are happening. So that's a lot of system functionality that you can expand out of existing components in your operation. At this point, I'm going to turn this the mic over to John Heun. He will then take on section 3.
Okay, hello. My name is John Heun. I'm a research specialist here at the University of Arizona, stationed at the Maricopa Ag Center, and I work for Pedro. My background is in electronic systems engineering, and I'm the person who put the electronic components together, as well as some of the mechanical fabrication to get these sensors mounted on the tractor platform. So now that we've gone over tractor platform and sensor considerations, now we need to integrate everything. So major considerations for system integration from my perspective is what sensors are we going to use? The sensors that were chosen for this project were the IRT for thermal, sonar for plant height, and spectral sensors, which were the crop circles. So another consideration, so some of the questions, what do we use for measurement and logging? What's a good system? How many channels are we going to need to get all these sensors hooked up? What we used was a Campbell Scientific CR3000. That's where we started, and we used that for our analog sensors, which our sonar was an analog output, current loop, 0 to 20 milliamp current loop, and our IRTs were also analog outputs. So we put those guys on the CR3000, and for the spectral side, we left those on Holland's GeoScout to run those, and I'll get into why we did that later. But these two logging systems were separate, but we were still linking them and synchronized at the same time with GPS position data. Another consideration: how fast do we take measurements? What's going to be the scan rate with this data logger, and what's possible and what is practical and necessary at the same time? Where are our limitations? Data logger, is it the sensor response? Is it perhaps the GPS output frequency, or is it the speed of the platform in the field? I mean, as far as productivity goes. So there are many possible solutions here, but what we're going to talk about is the one that we custom tailored for what we wanted here with a drought study, and talk about what we had to deal with regarding some of these hardware and software issues. Okay, so here we have a system diagram of our setup. We have our spectral sensors connected to our GeoScout logger. Information was stored onto a 256 megabyte SD card that in that unit, and then on our analog side we had IRTs and sonar units interfaced originally with our CR3000 because we only had a few sensors and plenty of channels on there. And then as we expanded the system, we ended up adding a CR1000 instead of going with a multiplexer or buying a larger capacity data logger. So to those two loggers, we added CF card modules, and they make storing and downloading data to the office PC very fast, and they're very convenient and well worth, I think, the $100 or so that they cost to add those to those loggers. Very convenient. So although there are some limitations to deal with on our Campbell units, I really love using them. They're probably my favorite piece of equipment out of all the equipment that we have here. They're built very well, very rugged, dependable pieces of equipment. They've been pretty much the backbone of our electronic measurements and all of the projects that we've been doing here at the university over the last 6 years. So here we've got all three loggers linked to a single GPS receiver, in which we have used both Trimble, an Ag GPS 332 RTK receiver, and also a Hemisphere Outback A320 in different seasons. And here we're splitting the signals on the cables, creating basically a parallel circuit carrying all the digital data. So let's talk about measurements and communication. Analog measurements can be done extremely fast, much faster than digital. And when I say digital, I'm talking about the serial communications. For higher rate sampling, and that's, relatively speaking, faster than, say, 2 hertz. It's a good idea to use sensors that have proportional analog output, such as a current loop or a voltage output, than serial sensors. So in our case, what I chose to do is not mix the digital and analog outputs in our application. We kept them separate and on their own loggers, and we paired similar sensors on the same logger, and so we had IRTs all on the CR3000 because it had more channels and we needed all those channels. And so with there not being any room left over, we moved all 4 of our sonar sensors onto the 1000. So for example, I experienced a case where adding a second serial port to the logger. So on the logger, we've got an RS-232 port, and those GPS signals are coming into that port and being read by the logger. And so what I was attempting to do was bring in another stream of serial data onto a separate port on the same data logger, both data incoming at 5 hertz. And what happened was that because of limitations in the data logger, my sampling frequency, which I had programmed for 5 hertz, could not go faster than 2 hertz. So that data logger is needing more time to handle strings coming in on more than one port. So trying to minimize that and just using the serial port for GPS was the best thing to do here. So I'll get into another important aspect of this a little later. Serial sensors will be the limiting factor of the data logger scan rate when trying to achieve higher rates while using analog sensor outputs at the same time. So they're just slower in nature than analog outputs. So the concept I want to highlight in this slide is that we can share one GPS unit with multiple data loggers and synchronize them by geographical position data. So I'm saying synchronize loosely here because depending on exactly when each data logger is in its scan cycle and it's ready and receives a complete GPS string, the GPS receiver may have updated its position, and one of the loggers or 2 of the loggers may grab a slightly different position, but it's a very small difference when we're talking about a speed of 5 hertz. Okay, in this example, we don't have to worry about too much about the specifics here, because this was for a different project in which we were using an RS-232 network on a grain combine before we did this phenotyping work. But just to illustrate a point that here again we're splitting up the same GPS string, we're using the same wire, and we're splitting it up to 3 different what I would say a listening device that only needs to record those GPS strings and doesn't need to send any kind of feedback information at all. So we can just share the same lines of communication and not worry about any kind of data interruptions or loss of information. So the voltages that are on these wires are high enough, and the resistances in the wires are small enough, and the cables are at short enough distances to be able to complete these without any kind of problems here. Okay, so we can easily configure the GPS receiver to output and send multiple strings over our RS-232 network here and choose which one we want to use and ignore the rest. So we typically use the GGA string with the Campbell's, and Holland's GeoScout data logger requires GGA and RMC strings for operation. So as far as programming on the Campbell side, simple is better. There's just less headaches to deal with. So I suggest picking a single string. We use the GGA string again with the best information for your particular purpose, and just go with that one. Now on this slide, we have our RS-232 network synchronizing our loggers and our crop circle sensor network, which operates a little differently. The crop circle spectral sensors communicate with the GeoScout logger over a serial network, which is a RS-485 protocol and similar in nature to a CAN bus. In this case, sensors are pulled for data so that only one can speak at a time, and we don't have any clogging of data on those lines. So information can move, in this case, in both ways on the same set of cables, so these protocols are implemented in order to prevent data loss. So what we chose to do was, instead of trying to integrate those sensors into the Campbell's, we chose to just keep it separate on its own data logger so that we could get the system operational and get to the field quicker. It's not impossible to get that done, but much faster, and we already had those components there. The main difference here, the main problem, I would say, with interfacing those sensors to Campbell's is that their baud rates, the speed at which data bits are passed on that network, are incompatible with the standard baud rates on the Campbell's. So there has to be basically another piece of hardware created to do that kind of an interface. So now let's look at these NMEA strings coming from the GPS and look at a couple common strings here and just see what kind of data are in them for those who aren't familiar with that. The first string we have here is the GGA string. So number one, we've got latitude data, and that's in the first two numbers are degrees, so that would be 33 degrees. And then the next two digits are 04, which are the minutes, the whole number, the integer portion of the minutes. And then we have the decimal point and then 8 digits after that, and that's the fractional portion of the minutes. So actually what the latitude here is 33 degrees, 4.42373 minutes north. And then we got the same thing, we've got longitude here, and then number 3 we've got quality. So for differential corrections, that would be a number 2, and in this case we have a number 4, so that's RTK corrections. Position number 4, that's 12. We've got 12 satellites there. Number 5 is an indication of the precision in the horizontal plane, and number 6, another important one, is our elevation above sea level. And then we've got the RMC string below that, some more redundant information here, latitude and longitude again. Number 9, we've actually got a speed in knots, and 10, we've got direction in degrees, and that's in relation to true geographic north. And then we've also got a date stamp there in position 11, which it could be useful, and the Holland system uses that particular one to set files. So, and then we've got the VTG string. So again, we've got direction, we've got 2 different speed values there. So let's get a little bit into software. Campbell loggers have an operating system that can compile their CR basic code, and they run measurement and control programs on them. The piece of code that I have here was designed to read in a single GPS string, which is the GGA string, and make sure that that logger is accurately capturing that entire string so that we can parse all that data out and get exactly what we want in a reliable way. So another important thing that it's doing here is making sure that all 8 decimal points in the previous slide, the minutes portion of the latitude and longitude data are going to be preserved. So I have to deal with Campbell's own data types for those of you who are familiar with programming. And in order to overcome that problem with the data types cutting off 2 digits of precision, so instead of, if you try to put that string and save it, parse it out and save it as a decimal point, it ends up cutting off 2 digits there, and those 2 digits are what get us into the centimeter level precision. So that was a pretty important thing to do in order to keep all those 8 digits. So what we did was just ended up breaking it up in a way where we're saving all of those numbers as whole numbers, as integers, so that we can keep all of the digits that are available there, and then we just put them back together in post-processing, which is a really simple procedure. So here's an example of an output file from a CR1000. In the red box, we can see the GPS information split up, and all 8 decimal digits are recorded, which you can see looks like an integer. There's not a decimal point there. Also, we have recorded other relevant and important GPS data in the other columns just to the right of that red box. In this example, in this part of the data here, the tractor is actually in motion, and if you look at the ELEV column, which is elevation, you can see that there's very small changes, at the centimeter level as that tractor's transversing the field. And if it was, this is RTK correction, so and you can see that in the quality column with the number 4 there. There's 4s all the way down, so we know that it's in RTK mode, and the very small differences in the elevation show that. So if it was differential correction, we'd have much bigger swings, up to 1 meter, 2 meters, even larger than that, which in our cases, for trying to calculate plant height, we need that really high level of precision. So also these other types of data, the quality, the satellites, the horizontal dilution of precision, those can help us troubleshoot and even filter out bad data if we had a problem with satellite coverage at a given time. Okay, same table here. We mentioned previously issues with sensor response, update rates, and sampling frequency. So here's an example where we had the data logger scanning the sensors at a rate of 5 Hertz, which you can see in the timestamp column there. So it was recording GPS positions, sonar sensor, and in this case, a laser ranger. So the sonar's update rate was set ASAP in its software, and the laser, which was also configurable, we set that update, I think it was about 100 Hertz. So if you look at that, both sensors are providing a current loop analog output, which is turned into a voltage using a precision 100 ohm resistor at the data logger. But what we're seeing here is the sonar unit's response limitation is about 2 Hertz. So we can see repeating numbers within a 1-second period of time, while we have a new number in the laser column every 200 milliseconds. So this can be undesirable, but also a benefit at the same time. Although we may want to have a 5 Hertz response from that sonar sensor, the important thing here is that we are not limited to sampling both sensors at 2 Hertz. We're not getting hung up by that sonar sensor because it's an analog input or an analog output from it that we're reading, and there's always a signal present in the current loop type analog output. So we've got flexibility here to make measurements at higher speeds to collect what we may deem more important data, like for the laser, for instance. So, but at the same time, it also brings a question that, is 5 hertz really a reasonable or necessary scan rate when one of our sensors can't provide new data that fast? So some things to think about there. Okay, so considerations. For data loggers, we're looking for something rugged, something field ready, can handle vibrations, has a, for a computer, is it a solid state hard drive, something that's not going to skip and get hung up. We want to save, we like saving to memory cards because we can easily move that data from the tractor to the office computer. Data loggers, the number of channels, how many sensors are we going to be using, how many channels are they going to need. Those IRT sensors, they take 3 channels each, and the sonar sensors, they take 2 channels each. So when you're adding a ton of sensors, those channels get used up pretty fast. So there's different options there. You can go with a logger with a bigger capacity, or you can break it up into smaller loggers, and you can use those loggers for different projects down the road instead of just using them for this type of an application, which for a smaller project that might be, like a CR9000X might be totally overkill for the kind of measurements you need. But we can save money and we can be resourceful, maybe use these loggers from other experiments that we've done, other data collecting events, and just bring them together for this kind of a project. And we can do that, and there's no problem doing that because we're going to synchronize all that data, which is measured independently by those loggers, with the same GPS signals. We should use analog sensors with analog outputs, current loops or voltage. Or current loops, we're just turning them into a voltage because that's what data loggers can measure. And we can do, we have that way we have the ability to make really fast measurements. I would suggest, as far as programming goes, keeping calculations to a minimum, save complex analysis for post-processing, just keep it simple. And then also on the safety side, these systems can get pretty large pretty quickly as far as the electronics go, so having a dedicated driver may be necessary depending on how you build the system and how much user interface is required during sampling. So there's only so much they can do, and it needs to be a safe operation. Some final remarks. A flexible design. This system has a very flexible design where we can use these loggers and all these pieces for other projects, and then we can reassemble and bring them together in the summertime to do these kinds of projects. And so we're not just limited by one type of hardware that can only do this and it can't do anything else for us. So we can be resourceful in how we put these things together. We're using existing equipment and materials. On the tractor side, we're using, instead of fabricating brackets and mounts from scratch, we're using things that are already available for the agriculture sector. We can just buy them, put them on, get the sensors on there, save a lot of time. They give us a lot of flexibility to be able to get things level or make adjustments and move them into positions where we think we would like to do sampling. On the electronics side, research your sensor specs carefully. Sometimes commercial claims can be a little deceiving. I don't want to point any names out or anything, but like if a sensor is they're saying better than 1 hertz of an update rate, then you shouldn't think that you're going to be able to get 5 hertz of a response out of that thing. So somewhere in the middle there you might be able to get something, but just be careful on that. And then just keep it simple. just keep it basic and don't go too crazy with trying to see what everything you can get, what's possible. Just start simple, and then you can move up from there. So then, as far as some of the work that we still have going on in this, we're working with our collaborators at USDA, ARS. We're exploring low-cost sensors and GPS options with Jeff White there. We're helping with some preliminary testing of a LiDAR system with Andy French and Bob Strand. And finally, we would like to thank Cotton Inc. for their support on this project. Thank you.